Good morning, champs. Until now, we mostly solve real integrals using circular contours. But sometimes, circular contours are not the best choice. Today, we will see a completely different contour, the rectangle contour. And this contour becomes natural because the function behaves very nicely under vertical shifts in the complex plane. We want to compute the integral from minus infinity to infinity of 1 over hyperbolic cosine of x. The final result will be pi. First, we extend the function to the complex plane. F of z equals 1 divided by hyperbolic cosine of z. Now comes the key observation. Hyperbolic cosine satisfies the identity hyperbolic cosine of z plus I pi equals minus hyperbolic cosine of z. Therefore, f of z plus I pi equals minus f of z. This is extremely important because shifting upward by I pi almost reproduces the same function. That strongly suggests using a rectangle of height pi. Now draw the rectangle from minus r to r on the real axis and height pi in the imaginary direction. Next, we determine the poles. The poles occur where hyperbolic cosine of z equals 0. Using the exponential definition of hyperbolic cosine, we solve this equation and obtain z equals I pi over 2 plus k pi I. Inside our rectangle, there is exactly one pole, z equals I pi over 2. Now we apply the residue theorem. The contour integral equals 2 pi I times the residue at I pi over 2. Since we have a simple pole, we use the quotient formula for residues. After substitution, we obtain the residue equals minus I. Therefore, the entire contour integral equals 2 pi. Now we split the contour into 4 parts. The bottom edge is exactly our desired integral. Now comes the beautiful trick. On the top edge, we replace z by x plus I pi. Using the shift identity, we get f of x plus I pi equals minus f of x. But the top edge is traversed backwards, so the two minus signs cancel. And the top edge becomes exactly the same integral as the bottom edge. This is the central idea of the whole computation. The vertical sides vanish as r goes to infinity because hyperbolic cosine grows exponentially. Therefore, only two identical real integrals remain. So we get 2 times the integral equals 2 pi. Hence, the integral itself equals pi. And this example shows something very important. In complex analysis, choosing the correct contour is often the entire problem.